This video contains the notes for section 8.8 on improper integrals, which sounds kind of scandalous, I suppose. So what is improper about improper integrals? Be the first question that I think we should answer. And the answer is that if you consider, for example, the function 1 over x squared. We know what that looks like. It looks like in the first quadrant, goes through the point 1, 1, and 2, 1/4, and so on. And it comes down and hugs the x-axis pretty quickly, pretty close, something like that. And well, what if we considered the area under this function from 1 to infinity? Well, that's certainly improper in the sense of geometric area because it's an unbounded area. It goes from here and then forever in that direction. And no matter how far you go, no matter how close the curve has come to the x-axis, it's still going to keep going, and there still will be a tiny sliver of area there, however small it is. So this is not a well-defined geometric area like our other areas where we go from, say, 1 to 2. And in geometry class, you would not be allowed to talk about this in the area of this because it's not actually bounded. So why would we be allowed to talk about something like this in calculus? Well, we have to make an argument first that an area like this could exist. Let's see. We could look at a series of rectangles that are all bigger than these areas. And this rectangle would have an area of 1, right, and the curves underneath that. This one would have an area of, 1/4, and this would have an area of 1/9. And then this one would have an area of 1/16, and so on. And we could also think about what we know about geometric series. I mean, we know that it's possible, for example, for a series like this, 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, and so on and so on. This is a geometric series, right? And as long as the multiplier to get from one term to the next is smaller than 1, or actually if its absolute value is in between -1 and 1, then we know that it does actually add up to something. And you can make a compelling geometric argument for this part. Remember, you can make a square that has sides 1, and you can divide it in half. There's half of the area, and then you can divide that in half. There's a quarter of the area. You can divide that in half, and there's an 1/8, and there's a 1/16, and so on and so on. And if you do that forever, you get infinitely many fractions like this, and clearly they're all inside this square. And if you ... then you can say this infinite series is actually equal to the whole square. So for example, this series would add up to 2, right? 1 plus the whole area of that square. And there is a formula for the area, or the sum of a geometric series, but we'll get to that later. We don't really need to know that or remember it right now. All I need to do right now is convince you that if this sum exists, then this area also exists. Let's look at the terms. The function here has an area less than 1, right? And there's the first term, same. This one definitely has an area that is less than 1/4, and this in 1/4 is less than 1/2. 1/9 is less than 1/4. 1/16 is less than this. 1/25 is less than this, and so on and so on. So whatever this area might be, it's trapped underneath a bunch of rectangles that have a sum that's even less than this that adds up to 2. So even though this area goes on forever, it does appear that it would exist. So how do we find it? Well, here's the good news. The good news is the actual calculus for doing this is not any different than what we've done before. So I'm going to write that as x to the negative 2 now. Let's just pretend that we're not scared of this infinity and just proceed as if it were any other integral problem. So what's the antiderivative of x to the negative 2? It's negative x to the negative 1. And we'll plug in, that's from 0 to infinity. We're going to plug in, quote unquote, plug in infinity, whatever that means, and hopefully it will work. So let's see. I'm going to take the negative sign to the outside, make it a little less likely to make a sign mistake. I'm going to plug infinity in here. It's infinity to the negative 1 minus 1 to the negative 1. Now, minus 1 over 1 is just 1. So the question is this: what does that equal to? Well, 1 over infinity, as something gets bigger and bigger and bigger, 1 over infinity is just 0, right? That goes to 0. And so I have negative 1, so that answer is the area is in fact equal to 1. And that we suspected that it existed, and we also suspected that it was going to be less than 2. So there you go. So here's the deal. If you have an improper integral of this type, where one of the limits is actually infinity, then if you go through the problem and when you plug in infinity you get something that just goes to 0, then you're good. You have found an improper integral that does exist. But if you try it with something and you get an improper, or you get an answer down here that doesn't exist, that means your area is actually going off to infinity. For example, what if we tried the area from 1 to infinity under, under 1 over x? Well, we'll do the same thing. We just proceed like it was any other integral problem. The antiderivative of 1 over x is natural log x. That's why I wrote that there. I was getting ahead of myself. And now we'll plug in, that's natural log of infinity minus the natural log of 1. And the natural log of infinity, although the natural log function grows very, very, very slowly as you go off to infinity, the natural log of infinity does keep growing at a tragically slow pace, but it does keep going up, keep growing. So this is infinity minus 0. So this is infinity, which means we say that this integral is divergent. It diverges. It doesn't converge to some area. It just doesn't exist. And you can, I think it's also fine to say that it does not exist. That area doesn't exist. Right? That might have been what we suspected here, that if you just keep going forever, you'll keep adding more and more area. But it turned out you're adding it in such a way that it behaves kind of like a geometric series. And we'll deal with this idea of the connection between calculus and geometric series a lot more in Chapter 10. But for now, our basic procedure is you just evaluate the integral and then hope for the best. And if you get an answer, if you get like a 1 over infinity, then you get an answer. And you report that answer. And if you get something that turns out to be equal to some version of infinity, then we say that that integral is divergent, or that it does not exist. Okay, let me just give you a couple more examples. There's another way in which we can run into these improper integrals. You might, if you think about it for a minute, you might be able to recognize that if we had, for example, the 1 over x squared function, we already talked about its area from 1 to infinity. We know that that area turned out to be 1. Well, what about its area from 0 to 1? What if we did this? First question is, why is that improper? It doesn't have an infinity here or here. But upon examining this for a second, you can see that we're taking area up against a vertical asymptote of the function. So although it's not going off to infinity here or here, the area is kind of being squeezed up to infinity as this asymptotically approaches the y-axis. So this is improper, right? It's improper because there's a vertical asymptote at x equals 0. So if you're right up against a vertical asymptote, or if you cross over a vertical asymptote, then you've got a situation where you have an improper integral. But, again, the good news here is that we just proceed like nothing's wrong. We say, right, the antiderivative here, negative x to negative 1, from 0 to 1. So let's say take the negative sign to the outside, and plugging 0, that gives me 1 over 0 minus 1 over 1. And here 1 over 0 goes to infinity, so we're in trouble. This is divergent. Sorry, I'm about to run off the page there. Divergent. So it didn't work here. It turns out that although this area exists, this area does not. Interesting. Let's see. How about let's try this one. Let's try the area under 1 over x from negative 2 to 2. It really does help to picture these things to see why they're improper. Well, it's the same situation as this, right? We're coming up against the vertical asymptote of the function. Now here, you might be in trouble because if you just blindly did this problem, you might not notice that you've jumped over the vertical asymptote. So what do I really have to do here is say, well look, this function is symmetric, right, with respect. Oh, actually, this is just going to be 0, isn't it? Ha ha ha. Bad example. That's going to be 0 because those two are equal areas on opposite sides. So let's try something else. Let's try from negative 1 to 2 instead, because that won't be equal to 0. So now we're talking about from here. So if it exists, it'll be some positive number. I'll have more positive area than negative area. Okay, now what I have to do is I have to split this into two different integrals. I have to isolate the trouble spot and then go from negative 1 to 0 and see if either one of these don't exist, then the game is over. So split it up into those two, right? Split it up over the vertical asymptote and then say, okay, so this is going to be natural log x. That's actually natural log absolute value x, right? Plus natural log, I don't need the absolute value here, but I'll throw it in anyway. Do need it there. So that's the natural log of 0 minus the natural log of the absolute value of negative 1 plus the natural log of 2. I don't know why I put that in absolute value signs. That's kind of silly. Minus the natural log of 0. Now you have to be careful here because this natural log of 0 here, if you remember what the natural log function looks like, it plunges down to negative infinity. So the best we can do here is say that that's negative infinity, and as soon as we get that, game over. This is divergent. So I think that you now have seen everything that you need to see for improper integrals. We can try a few examples and see how that goes. But the nice thing about them is the actual calculus is not any different. You just take your antiderivative, plug in the numbers, and watch out for infinities that pop up there. If you get an infinity that goes down to 0, then you're fine. But otherwise, you're in trouble and you have to report that it's divergent. How do you know when you're doing an improper integral? Well, if one of the limits of integration is actually infinity, well, that's the most obvious kind. And the other kind would be if you are going right up against a vertical asymptote or you're going across a vertical asymptote. Okay.